Um, Hello, everyone. I'm Winjie Pan, and I'm going to present the tuning of vectorization in Graal today. Uh, my name is Winjie Pan. I'm a third-year PhD student in computer architecture at University of Michigan, and I was the intern at the Twitter VM team in last year's summer. So this work is done during my last summer internship. So the outline of my presentation today is to first have a recap of the Graal and the autovectorization. Secondly, I'll discuss what's the challenges in autovectorization and how would we deal with that. Next, I'm going to show the autovectorization performance on several benchmarks. And finally, we'll discuss what's the next step of the autovectorization in Graal. So first, let's just have a quick recap of the vectorization. Let's look at the simple example of the code here. It's adding two arrays A and B and storing the results into a new array C. So after we unroll the loop by a factor of 4, it could actually transform the scalar version of the code into a vector instructions. Which we are accessing since we have accessing the memory times as reduced, we could see speed up of the overall speed up of this code. So actually, autovectorization has already been implemented in many compilers, almost all of the compilers. But for Java compiler, the CPU has enabled the superword level parallelism. It will first unroll the loop partially or fully, and then seek isomorphic tags, and then transform those tags into vector instructions. The Graal Enterprise Edition has also implemented autovectorize. However, it is not open source. For C++ compiler, for example, LVM has implemented the SLP vectorizer, which is the superword level parallelism vectorizer, and the loop vectorizer. The SLP loop vectorizer could merge multiple scalars that are found in the code into vectors, while the loop vectorizer focuses on the loops that tries to widen instructions on loop on multiple consecutive iterations. For the previous example, that adding to array elements wise, both the SLP vectorizer and the loop vectorizer could successfully detect them and transform them to vector instructions. So the current status of autovectorization in Graal is that the Graal Enterprise Edition has implemented this. However, it's not open source and it charges money. And the Graal Community Edition, it has so far it has not implemented autovectorization. The Twitter VM team, so Nick and David, they have previously worked on enable the superword level parallelism and support the Intel SSC and AVX instructions. And thanks to the work, and I could continue to work on the autovectorization in Graal. So what's the SLP algorithm? I'll use a simple example of the paper to go through this. So the SLP algorithm will first unroll the loop if it's needed. And this region of code is already be unrolled. And the next step is to identifying adjacent memory references. So in this example, the instruction 1, 4, and 7 are accessing the same array A by index I plus 1, and I plus 2. So after we found those seed instructions, in the next step, we're trying to extend the pack list. We found that the variable B is used by instruction 3, and variable E is used by instruction 6, and 7 is used by instruction 9. So we'll pack them together. And next step, still we found that the user, so in instruction 3, C is defined by instruction 2. Similarly, we'll pack those into like this highlight in the blue box. After we have combined those packs into 3 packs, well, in the next step, we're going to filter the packs to find if they're profitable or not. to do so. If we found that they are profitable to transform from the scalar version to the vector instructions, we are generating the vector instructions and then turn it into machine code. Okay, so in the next section, I'm going to discuss what's the challenges in autovectorization. So first is the discoverability of the vectorizable loops. Some of the pre-vectorization phases or optimizations may have some side effect on the autovectorization that may prevent us prevent autovectorization to potentially use those regions of interest code. For example, the bounce check for memory access, or there's some pre-vectorization phase that tries to commute inputs. Those will unexpectedly avoid the autovectorization to be used. And another challenge is to how to determine the region of interest of vectorization. Some kind of code, maybe it's not profitable to use the vector instructions because maybe the overhead of packing and unpacking outweighs the benefits of using vector instructions. In this way, we just want to find a cost model for vectorization to identify those cases. And also there are challenges in the hardware support, but I'm not going to focus on that in this talk. I will elaborate the pre-vectorization phases and optimization, and also the cost model in the following slides. So first is the pre-vectorizing phases, which is bounce check elimination. So before the Graal inserts the bounce check for array access to check, for example, in this for this code, it needs to check if the index of I is if it is existed the size of the arrays to ensure the correctness of this program. However, this bounce check exception will disable the loop unrolling, and loop unrolling is the prerequisite of the superword level parallelism. So the hack around this before is to unroll the loops earlier before the guards are lowered, or just remove the bounce check. But of course, this is problematic. It may cause the exception, the bounce check exception. But after the bounce check elimination is available in Graal 20.3, the problem is solved. And another thing that may prevent the autovectorization to take place is that some of the pre-autovectorization phase will commute the inputs for commutative operators. For still, it's the same example code. Actually, we would expect after we unroll the loops by a factor of 4, we would expect the compilers to generate a vector read for array A and a vector read for array B, and also a vector read instruction. Finally, there's a vector write that's read back to array C. However, in some of the phases, it will try to swap the orders of these two inputs. So which is highlighted in the yellow. It will swap the order of BI plus 2 and AI plus 2. This will not change the final output of CI plus 2. However, if we apply the autovectorization in this case, it will cause redundant vector extract and then vector pack to form those two packs of AI plus 1, BI plus 2, and AI plus 3, and also another packs in need for redundant vector extract and vector pack. So after, we could expect that after having those redundant vector instructions, the code after autovectorization optimization will be slower than the original scalar version of code, which is, we do not want this. So the superword level will slow down if we commute inputs. A quick fix is just to disable commute inputs for memory access. When we found this, when we found the compiler tries to commute inputs, we just disable that. But this is done before the autovectorization phase, which means it may have side effect on other optimization. A better choice is to use a look-ahead SLP. So the look-ahead SLP tries to reorder the inputs for commutative operations to find a more profitable paths for vector instructions. It is done at autovectorization phase, so it will not have side effects for other optimizations. So for the example listed here, CI and CI plus 1, these are adjacent memory access, and the plus operator, the add operator is a commutative operations. So the compiler will detect that if we swap the order of BI plus 1 and A plus 1, we do not need extra vector, a vector extract and a vector pack, that we have better performance if we use the autovectorization. Okay, after talking about the pre-vectorization phases and optimization, let's look at the autovectorization phase. So when it is profitable and when it's not profitable to vectorize. So for example, this region of code, is just accessing AI minus 1, AI and AI plus 1. And it seems that we are accessing adjacent memory, so we can use a vector read. However, actually we'll need extra vector extract to extract the scalar value from the vector register. We have 3 vector extract here and 1 vector read. And overall, the overhead is higher than the benefit. So the vectorized version of this code is slower than the original scalar version. So when it's not profitable to vectorize, it is when we use the uses of vector operations on not vectors. That means we need actual vector extract. For another case that is not profitable to vectorize is that when we found the inputs of vector operations are not vectors. Let's look at the example here. AI equals AI plus B2 multiply I. The reading and storing values of array A, we are accessing the adjacent memories. So there are 1 vector read and vector write, which looks good. However, when we're accessing the array B, we're accessing a non-adjacent index. So we need 1 extra vector pack, and overall the vector pack overhead is higher than this vector read and vector write. So when the inputs of the vector operators are not vectors, we need extra vector pack here, and it's not beneficial to enable the autovectorization in this case. However, there are some exceptions. If AI equals AI plus 1 or plus a loop invariant value, for example, a size here, actually the global value numbering phase optimization will host this constant or loop invariant outside the loop. So the overhead of packing the constants or the loop invariants into a vector register is amortized. So we'll think it is profitable in these cases. And in next sections, I'm going to show the results of autovectorization on several benchmarks. We're using the Graal 20.3 version and testing on Mac OS x86-64. We're having 4 settings: C2 with superword, and C2 without superword, Graal with and without autovectorize. Okay, the first, this slide shows the M flops of the SciMark2 benchmark of the Graal without autovectorize or the Graal with autovectorize using different cost model. So the old cost model means that we just aggressively apply autovectorization when we found maybe it's could vectorized. But the new cost model, we just said that we found if we found the cases that it's not profitable to do so, we just disable the autovectorization. the y-axis is the M flop, so the higher the better. The first bar shows the scalar version, it's the Graal without auto-vectorize. And the second bar shows the result of Graal with auto-vectorize, but we just aggressively to do so. Except the FFT, all the others, it seems that the auto-vectorize is worse than the scalar version. However, when we use the new cost model, like considering the not beneficial cases, we found that FFT, we still could see the benefit of auto-vectorization, but for other cases, the final code will have similar or better results compared with the Graal without auto-vectorize, compared with the first bar. So the takeaway is that our new cost model will avoid vectorizing non-profitable instructions. Okay, the next slide shows the speed up of on a benchmark that is designed specifically for vectorization. This is to detect multiple float arrays benchmarks. The y-axis is the speed up, which is normalized to C2 without superword. So the pink one is just normalized to 1. And the red one is the results with C2 of C2 with superword. So we can see that there's for some of the benchmarks, C2 with superword has better performance than the C2 without superword, which means they are vectorizable patterns. The third bar shows the Graal without auto-vectorize. It's the scalar version of Graal. And finally, the dark blue bar shows the performance of the Graal with our auto-vectorize. We can see that for most of the cases, when C2 with superword could detect the vectorizable versions and successfully transform to vector instructions, it has better performance. The Graal could also, the Graal auto-vectorization could also detect those. So we can see they have the similar speed up. So the takeaway is that the Graal with auto-vectorize would speed up the vectorizable patterns. And the next slide is similar, but this benchmark is for multiple integer array benchmarks. So we can view the similar patterns here that the C2 with superword could have better performance over the C2 without superword on some of the workload. And our Graal with auto-vectorize could also detect those patterns for most of the cases. That is highlighted in red box. But for these two workloads, the Graal without auto-vectorize and with auto-vectorize has similar performance. That is because we have not enabled the shift vector instructions in the backend, but this could be fixed if we support those instructions later. So the takeaway is the same, that we could speed up vectorizable patterns. Next, this is the result of the ops per second for a Java matrix benchmark, which is the add operation up to matrix and store the results into a new matrix. The axis here are the Java linear algebra libraries from COBS to OJL. The y-axis is the ops per seconds. The higher, the better. So still, the pink one is the C2 without superword. Red one, C2 with superword. Graal without auto-vectorize. Graal with auto-vectorize. But we have different on-row factors here. Surprisingly, C2 or Graal, actually the superword or auto-vectorize does not have a lot of speed up compared with the scalar version. And if we look at the EJML, when comparing the third bar and the fourth bar, actually the auto-vectorize do not have much benefits over the scalar version, because the on-row factor is 4, which is limited to the vector register lane. So if the vector register is 256 and data type is 64, we only the on-row factor is limited to 4. But if we remove such limits and look at the green bar here, this U unroll factor is 8, and we could view a much higher speed up over the Scala version. So that means the unroll factor matters for autovectorization, and loop unrolling is a phase that is before autovectorize. But why would we have only no or only slight speed up of the autovectorize optimization? So I just try to analyze the reason. So the code for the matrix add is very similar to the array add, that is getting the value of matrix A and B, and the results is stored into a new matrix at index I. So if we look at the auto-vectorized assembly code here, when the unroll factor is 4, because of the dependency of the add instruction and reading memory and writing memory, we have the throughput around 23 cycles per iteration. That's the only rough estimation. But if we unroll with a factor of 8, this reading memory access are independent of each other. So it could be issued just 1 cycles after previous reading instructions. So in this way, we could achieve, these two are independent of each other. So in this way, we could achieve 24 cycles per iterations, but the throughput is double because the unroll factor is larger. However, if we look at the assembly code without auto-vectorize, but still we unroll the loop by a factor of 8 because the CPU is operated on a pipeline manner. This like reading and adding and storing, these 3 sets of instructions are independent of each other. So overall, it will take 34 cycles per iterations. So compared with the assembly code with auto-vectorize, but unroll factor is smaller, which is 4, we can see that the Scala version actually has similar throughput as the auto-vectorized version. So my guess is that because the programs are bottlenecked by memory access and loop carry dependency. So if we do not have enough unroll factor, the benefit could not be fully utilized. So the possible solution is that whether we increase the unroll factor and also, or we will take the cycles per iteration estimation into consideration of the cost model. So to decide whether we need larger unroll factor or not. And finally, I'm just going to talk about what we could do for autovectorization in the future. So their existing cost model is C2-like cost model is a veto, which we have already implemented and talked about this. So we have found if it's not profitable to do the vectorization, we just disable that. And also there's an LVM-like cost model. There are estimated the vectorization instruction cost and the Scala instruction cost. And to calculate it, it's profitable to do so or not. And a more advanced recent research has used an ML-based cost model, which is called the neural vectorizer. It uses a deep reinforced learning to determine the vectorization factor. It works on the loop vectorizer that determines the numbers of the unroll factor and the interleaving factor. So could we feed, for next up, we're asking this question. So could we feed hardware support and latency to the cost model? Like, should we consider the unroll factor, the latency, and the throughput of the instructions at the assembly code, like we discussed before? And could we use the machine learning model as the cost model? As simple as linear regression or more complex model, like neural language processing, transformer, graph, neural network, etc. But we need to be aware of the overhead of such machine learning model inference at runtime. And could we also have vectorized more using dynamic profiling for this region of code? If we're using the profiling to find that for most of the time, the step is 1, actually we could vectorize this region of code so that we can have utilized more of those vectorizable patterns. Okay, that's all of my talks. And I want to thank the Twitter VM team and especially Uma for the great mentorship during my last summer internship, and thanks Nick and David for their previous work on the Graal autovectorization and their help. And yeah, that's all of my presentation today. So I'm really happy to answer any questions.
Thank you, Yunji. That was an awesome presentation, even if I say so myself. I don't see any questions in chat. And clearly the Twitter folks don't have any questions for Yunji. Are there any questions from anybody else in the audience? Feel free to raise your hand. Offer any comments, thoughts.
One quick question. Do you have found any real world kind of benchmarks or use cases where vectorization in Java really pays off? So you have some, I don't know, machine learning code or so, because for us, it's quite often it's like, yeah, all this vectorization works very well on small micro benchmarks, but then when you look at real world code, it's like, it's very difficult to find anything that really profits from it. So I'm wondering if you have anything inside, outside of Twitter that really benefits from the vectorization.
Yeah, I have not tested machine learning benchmarks because I guess many like machine learning models are written in C++. So there's not a lot like benchmarks that focus on the Java machine learning code. And I think also this the previous like the Java matrix benchmarks may be a little bit representative because for many machine learning models, they're basically matrix multiplication. So I guess if we could have results over the Java matrix benchmarks, it may be like a little bit helpful to understand the machine learning model.
Yeah, to add to that, yes, Christian, we are also struggling getting hold of representative applications or benchmarks that that would benefit from vectorization. One of the things that we tried to pursue, but we didn't get very far because we didn't spend enough effort in it, is this use of Spark, the Spark libraries, and whether we could get something out of auto-vectorization as opposed to the application level vectorization that is already being kind of experimented with. So, I mean, I see a potential opportunity there, but I frankly haven't had the time to kind of focus on that. So if there's anybody else interested in evaluating the Spark models and libraries, I think it may be worthwhile. Okay. Any other questions or thoughts?